Hey, I'm Eric. I can tell you about RL and RLlib. So this tutorial is going to be an overview of RL and RLlib with a focus on applied reinforcement learning, understanding how to model problems as RL environments, and how to use RLlib for distributed training and simulation. So clearly you can't overview RL and can't learn all of RL in 10 minutes. So there's a lot more documentation online, in particular with the overview of RLlib and also like links to the API, algorithms, examples, and so on. So I think it's first good to understand the difference between reinforcement learning and supervised learning. So in supervised learning, this might look pretty familiar. You're trying to train a model given some data set of labeled data. For example, here are images and labels for these images. And the goal of supervised learning is to try to predict the correct labels for all this data. Right, so you can train your model and you can deploy it and make predictions, such as here's an input cat picture and it can output the right category, right? So it's pretty easy to see how this could be useful for many applications. But in some settings, actually reinforcement learning is a more natural fit. And here's one example of a setting. Like say you're trying to develop a web application where you have users and they're interacting with some service you're developing. And the users might be doing things like searching for items, and then your service provides some results. They might be adding items to some cart, and you might provide suggestions. And eventually, they might buy some items using your service. So this sort of interaction has a very natural mapping into the reinforcement learning formalisms. You can see the users as the environment, and your service as the agent that you're trying to train. So users are going to provide observations to your agent, and your agents are going to provide actions that try to basically maximize the reward, or in this case, revenue. So really the difference is reinforcement learning is centered around interaction with the environment, where your agent is not just making predictions, but is actually taking actions that affect the environment and getting returns from the environment and trying to hopefully improve its performance over time. So there are a growing number of applications of reinforcement learning, and one of the first successful examples of deep reinforcement learning is AlphaGo from 2016. And you can see playing the game of Go as a reinforcement learning problem pretty simply. The observations are the board state, the actions are where to place your stone, and the reward is whether you win or lose the game. So there's, of course, other applications of RL. Here's an example from systems. So it turns out you can use reinforcement learning to optimize database queries. So it's something that's traditionally been done with hand-engineered algorithms and heuristics, but RL has been actually sometimes being state of the art. And you can see this is a RL problem by seeing the observations as the relations joined so far for a particular query, and the set of remaining relations. The actions are what relations to join next, and the rewards are the cost of the query or the runtime of the query at the end of the day. We can also use RL to synthesize data structures. For example, the state might be the current data structure, and the actions are whether to cut or partition it, and the rewards might be some metrics on the data structure. So you've seen the difference between RL and supervised learning, but there's many commonalities. So I think one thing particular note is it requires a lot of training data, because at the end of the day, you're training a deep policy. So for supervised learning, you need labeled data. For reinforcement learning, it's kind of easier in some sense that you could generate data yourself through simulations. So you don't need a data set, you can just generate data out of thin air, or by interacting with the environment at large scale. But both supervised learning and reinforcement learning do require scalable software libraries for training as a result of this. So that's where RLlib comes in. RLlib is a framework for scalable applied reinforcement learning. It's one of the machine learning libraries built on top of Ray. And it provides application support for many different types of reinforcement learning training, abstractions for both its internal RL algorithms and also if you want to develop your own, and also, of course, distributed execution with Ray. It's a unified framework for scalable RL, so thanks to Ray, it can implement many different types of distributed reinforcement learning architectures, all basically within the same system, and still achieve a very good performance. And I think this is a bit outdated, but we have a broad range of scalable algorithms basically all the best-in-class algorithms for reinforcement learning. So for reinforcement learning, there's many APIs you might want. Of course, you have the basic training and simulation, but you might also want to train on offline data collected from applications, or you might want to model more advanced problems with multi-agent reinforcement learning. And as an open source project, RLlib is doing pretty well. We have a growing number of users. So here's looking at 2018 versus this year. So more than doubled the amount of user interactions on GitHub. And here's a slice of the users using RLlib. So before we go into tutorial, how do you actually use RL to solve your problems? Well, as a quick reminder, the goal of reinforcement learning is to learn a policy function, here the pi theta function in the middle, that produces an action given some observation. So in this example, you have as an input some observation. If you're trying to train some racing car or something, it might be an image of what the car is seeing, and the action might be turning left or right. So the first step, and actually this is actually the most important step for most applied problems, is the problem setup. So you need to define the environment, what types of actions your agent can take. This might be a simple choice of a couple actions, or it could be a vector action or a more complex action space. You need to define the observations your agent is going to see. It could be just a numeric vector, an image, something more complicated. And of course, you have to actually implement this environment yourself. And then you have to choose an RL algorithm. Hopefully, you're choosing it from a library. And you need to define a policy that, some neural network architecture for your agent. The next step is collecting experiences. This is the interaction loop of taking your agent, telling it to compute some actions, letting it interact with the environment, and getting return and repeating this process. And then you want to improve the policy. So at a very, very high level, you want to improve the policy network by improving the probability of taking actions that lead to good rewards. So you can do this with SGD. Fortunately, a lot of libraries such as RLlib manage this process of distributed experience collection and policy improvement for you. And yeah, if you want to learn more, there's documentation. There's many good online courses on RL here. Here's one from Berkeley. So for this tutorial, we're going to cover kind of the basics of setting up RL environments, understanding how they work, and training with RLlib. So the first exercise will be just getting familiar with RL environments or Markov decision processes. The second is training a PPO policy in RLlib. And the third exercise, which is optional, is how to create a custom RL environment and how to tune the rewards to try to encourage learning. So if you haven't yet, you can find the tutorial on CodeLab. Go to that website, click the reinforcement learning with RLlib link, and that should open in CodeLab.